All right, today we have a long section, I think. At least it seemed pretty long. Was in Chapter 9, Section 2, the addition rules for probability and odds. Now there are a lot of good examples in this section, and please go and at least look at them, read them. Uh, the the parts that aren't examples, I suppose, so the actual text. But we will read some of the text because it is pretty important. So starting off, we read that two events are, just gonna laser, two events are mutually exclusive if they cannot occur at the same time. And that's the definition. If they cannot occur at the same time, then they are mutually exclusive. And the example given here is if you have a set of cards and you can only select one card, right? Jack and sevens, they're mutually exclusive because you cannot draw both a jack and a seven in one draw. Um, believe that should be good. All right, so real quick, let me try to reiterate mutual exclusivity. Uh, I guess I mean the definition is pretty good by itself. And actually, for the sake of it, let's just go ahead and snip this, and we'll put it on our notes, but we're gonna make it really large because that's I think that's the only time we actually see this. Um, well, we might not, but it's definitely a good way to see the definition of mutual exclusive. I don't think we have another definition of it. Yeah, okay, we don't. All right, so again, something is mutually exclusive if two events cannot occur at the same time. So let's just start off with here example one. All right, so example one, determine whether the events are mutually exclusive. So given that we have 1, 2, 3, 4, and 5 in set A, and set C is 3, 6, 9, 12, 15, and 18, are the events in A and C mutually exclusive? Okay, so can can something happen in one set? Can it pick a number in one set that doesn't occur in the second set? Well, not necessarily because both sets have a 3, so they are not mutually exclusive. They would be mutually exclusive if they cannot occur at the same time, right? In this particular case, we have a set with the number 3 and a set with the number 3. They both have 3 in them, so they are not mutually exclusive. So let's go ahead and put, let me fix my screen. Okay, so the events A and C are not mutually exclusive. Looking at example 2, more examples. And of course, Venn diagrams are used, and I guess I'll go ahead and snip the Venn diagram for the first example there. Let's go back and put that in. Okay, so again, we're just basically looking for the intersection, right? We talked about the intersection before. If there's an intersection between these two sets, then that means that they are not mutually exclusive. And so looking at this, we'll go ahead and just snip this Venn diagram, I guess. Looking at the Venn diagram, we can tell that we don't even need the Venn diagram though, right? We can tell by just looking at the elements here that they share the number 20. So by sharing an element, then they are not mutually exclusive, right? In order to be mutually exclusive, they must be um, what's the word? Unique, right? I mean, well, that's about it. I'm not gonna elaborate on that. I think that does a good job by itself. All right, so we know Venn diagram here. So in one trial of a coin toss experiments, excuse me, are the events getting a head and getting a tail mutually exclusive? Well, when you toss a coin, how many outcomes can you have? Well, you can only have one outcome, right? And it's either going to be heads or tails, right? So in this particular case, yes, they are mutually exclusive. Um, I don't think I really need all these cards, but I guess we'll put them in there. Didn't even snip everything. Let's try that again. There we go. Alright, so this reads, in one trial of drawing a card from a deck of 52 cards, one trial, are the events drawing a 9 and drawing an 8 mutually exclusive? And a standard deck of cards looks like the following, okay? So, is it mutually exclusive? Well, if it says one trial, so that means, one drawing, right? Um, are the events drawing an 8 and drawing a 9 mutually exclusive? Well, when I draw one card, I can't draw both an 8 and a 9, right? So, yes, they are mutually exclusive. If this seems pretty easy, it gets a little bit harder at the end, but not much harder. So let's think about this. So in one trial of rolling a single six-sided die, are the events observing a 2 and observing a 6 mutually exclusive? Well, when I roll a die, right, I can only have one side up, right? And whether it's a 2 or a 6 or anything else, I'm only going to see one number. So in this particular case, the observing a 2 and observing a 6, they are indeed mutually exclusive because I'm only going to see one and not both. Right. Next up, we have the addition rule for probability. So this is where we're going to get just a little more complicated, and a little more mathy, but it's something that I think you can handle. So if two events A and B are mutually exclusive, there is a simple rule for calculating the probability that A or B will occur. So the addition rule for probability of mutually exclusive events. If two events A and B are mutually exclusive, that means the probability of A or B is equal to the probability of A plus the probability of B. If we write that in set notation, it can be written as the probability of A, and again, we have that U, union, B, which is again, or, right, is equal to the probability of A plus the probability of B. So in words, if two events are mutually exclusive, you can simply add their probabilities to obtain the probability of an outcome being an A or B. So we're just going to add probabilities. So let's put that into practice here. And let's just go ahead and put this on the same page so we can just kind of follow along with our formula there. All right, like so. Okay, so example 6 reads, finding the probability of mutually exclusive events. In one trial of rolling a single six-sided die, what is the probability of observing a 2 or observing a 6? Okay, so what is the probability, first of all, of seeing a 2? So the probability of rolling a 2, probability of, I'm not going to put P of 2, so we're going to say rolling a 2. So we're going to say rolling a 2. Let's just put R2. I think that would look better actually. So the probability of rolling a 2. Okay, so what is the probability of rolling a 2? Well, on a six-sided die, there are 1, 2, 3, 4, 5, 6 numbers, right? I don't know why I did that with my hands, not like y'all can see, but there are 6 numbers. So there are obviously 1 in 6 odds of rolling a 2. Well, what are the probability of rolling a 6? Well, the probability of rolling a 6 is the same thing. It's 1 in 6. Okay. Well, our addition rule here states that in order to find the probability of both, we just have to add them. So we're going to take 1/6 plus 1/6, which is equal to 2/6, which can be reduced down to 1/3. Right? So there is a 1/3 probability of rolling a 2 or a 6, and of course we can figure that out easily. Also by saying, well, 2 and 6, that makes up a third of the numbers, right? The other numbers being, 1, 3, 4, 5, and well, we can kind of do some mental math like that too. But if we were to follow along with how the textbook is presenting this, I guess this is like a Common Core math. If we were to follow along like with this, then this is how we would set this up. Alrighty, so when selecting one card from a deck of 52, what is the probability of drawing an 8 or drawing a 9? Okay, so we could do this in one of two ways. The way the textbook will probably want us to do this is to do the whole, is to do the probability of drawing. We're going to put D8, drawing 8, plus the probability of drawing a 9, and that's equal to the total probability. And we're going to do it this way as well. So what are the probability of drawing an 8? Well, in a deck of 52 cards, there are 4 suits, and there's a number of each suit, right? So there's going to be a 4 in 52 chance of drawing an 8. There's also going to be a 4 in 52 chance of drawing a 9. So we add that together, we get 8 out of 52. 8 out of, that's not working out. Let's try this. 8 out of 52. If we reduce that, we get what? 4 to 26, 2 to 13. So 2 out of 13. So 2 in 13 chance of drawing an 8 or drawing a 9. And again, if we did it not the textbook way, we could say, well, drawing an 8, there's 4 8s, there's 4 9s. And so 4 plus 4 is 8, and there are 52 cards, and we could jump straight to this point right here. Right? But it doesn't really matter because we get there no matter what. Example, okay, so maybe it's not going to be as long as I thought. Yeah, well, here we go. So probability of non-mutually exclusive events. So non-mutually exclusive events, the way they work is, let's snip this while I try to collect my thoughts here, how I can explain this. Maybe I can just do straight to the example. Yeah, we'll just jump straight to example. I think the example does it better. Okay, so we'll do the same way we've done before, which we'll put the definition up here and then follow along with the definition with the example. So let's go ahead and start with the definition. So the addition rule for probability of non-mutually exclusive events. If A and B are mutually exclusive events, or not, I'm sorry, if A and B are not mutually exclusive events, then the probability of A or B is going to be equal to the probability of A plus the probability of B, which we've seen before, minus the probability of A and B. So what does that mean? Well, if we put it in notation down here, we use the union for or. That would mean the probability of A or union B is equal to the probability of A plus the probability of B minus the intersection of A and B. Okay, so we're gonna try and do example 8 real quick, and then I'll bring in our Venn diagram, because the Venn diagram really helps drive this home. So, but let's just try to work our way through this with our brains first, though. Reading the problem, suppose we select a card from a deck of playing cards. Okay, so we're going to select one card. What is the probability of drawing a diamond or drawing a face card? Okay, so let's try to follow along with this, with our notation above, right up here. Well, y'all can't see, I'm circling in white. Right up here, we're going to try and follow along with that. So what is the probability of drawing a diamond? Right. Well, if there are 52 cards in a normal playing deck, and each suit makes up a third of it, right? So there's gonna be 13. So the probability of, we'll put drawing a diamond. So drawing a diamond. Those are the worst D's I've ever written in my life. Drawing a diamond. What is the probability of drawing a diamond? Well, like I said, it's going to be 13 out of 52. Okay, and what is the probability of drawing a face card? Okay, well, how many face cards are there? Well, you have your king, queen, jack, and those are the only face cards. But of course, you have to do it 4 times, right? Because of each suit. So 3 times 4 is 12. So there is a 12 in 52 shot of drawing a face card. Okay, so here's where the problem comes into play. there is overlap with drawing a diamond and drawing a face card, right? What is that overlap? Well, the overlap would be the king of diamonds, queen of diamonds, and jack of diamonds, right? So there are 3 cards that overlap both of these sets. We must subtract those 3. Okay, because otherwise we'll be counting it twice. If we counted all the diamonds and then we counted all the face cards, we'll be counting the king of diamonds, queen of diamonds, and jack of diamonds twice. One moment. All right. Um, so those 3 we must subtract. Okay. So let's go ahead and so say how should we write this? Okay. Well, we'll just put it up here. So there are 3 out of these 52 that overlap. So the way we set up this problem is we just say 13 out of 52 plus 12 out of 52, and then we minus 3 out of 52. And then we do the arithmetic. 13 plus 12 is 25. 25 minus 3 is 22. So we have 22 out of 52. And of course, we can reduce that to 11 out of 26. Okay, so there's 11 and 26 chance of drawing either a diamond or a face card. Now, let's go ahead and, well, let's probably going to put this on the next page, but this really shows what I'm trying to say. Of course, you probably already, I think you got it, but I'm going to snip it anyways. So drawing a diamond here is set A, and of course these are all the diamonds. And drawing a face card here is set B, and these are all the faces. Well, the king, queen, jack of diamonds appear in both sets, so we can't count it twice. And so that's why we subtracted that 3, those 3 cards. That's why we did that here. We subtracted 3. Okay. Okay, so same deal. We're looking for the probability of non-mutually exclusive events. So you have a container with balls numbered between 1 and 20. If you randomly draw a ball from the container, what is the probability that the number on the ball will be divisible by 3 or divisible by 4? Okay, so first of all, we have to figure out, okay, so out of these numbers, what are the numbers that are divisible by 3? Okay, so let's go ahead and put, well, let's say divisible by 3. So D3. The numbers that are divisible by 3 are 3, 6, 9, 12, 15, and 18. The numbers divisible by 4 are, what's 4, right? Yeah. Are 4, 8, 12, 16, and 20. Okay. So looking at our probabilities here, so the probability of rolling a 3, put this down here, so the probability, not rolling a 3, the probability of drawing a 3 looks to be 1, 2, 3, 4, 5, 6. There are 6 of them. So 6 out of 20. The probability of drawing 1 divisible by 4 is 1, 2, 3, 4, 5. So 5 out of 20. Okay, but we're not done because there's some overlap. Well, I say some. There's one overlap, okay? And the overlap is this 12. So what we're going to do is we're going to subtract that overlap from these 2 sets. So we're going to subtract that 1. Okay, so we would say, looking here, we would say 6 over 20 plus 5 over 20, and that is equal to, not equal, I'm sorry, minus 1 over 20, because we have that 1 overlap, right? And that is equal to, well, we have 11 minus 1 is 10, so 10 over 20, or in other words, 1/2. And everything's just falling apart here. Let's try that again. I don't know if that's better, but there we go. Oh yeah, I was gonna fix that 0. My zeros are not the best. My arm gets fatigued. Okay. All right. So there we go. All right. Next up, we're gonna talk about. Next we're gonna talk about the complementary rules. So complement, C-O-M-P-L-E, right, basically means what's left, what's on the outside. Right, you might have heard about it in your high school geometry class, but the probability law for complementary elements, let A be some sort of event, and it has a little apostrophe there. That means complement, and A complement be the complement of A, obviously, right? Um, but then the probability of A plus the probability of A complement is equal to 1. So again, A complement is just basically what's left over. And let's go and look at an example real quick so we can um, really show what we're trying to do here. All right, so this problem reads, an airline reported that 92% of its flights arrived on time, which means the flights arrive on or before the scheduled arrival time. What is the probability that a flight will arrive late? Well, um, if they arrive 92% of the time on time, and everything adds to 100%, then 8% of the time, because 100% minus 92% is equal to 8%. 8%. Oh gosh, 8%. There we go. Okay, and I mean that's it. That's the whole idea of complement. It is what is left over in the set. Um, yeah, that's about it. Although I will say, I'm going to go ahead and snip what the textbook put. But to me, I don't know. I think I'd rather do it the way I did it. And I think this is the final part. Is going to be finding the odds. Odds that something may happen, especially something that's happening really big, at least across the country, is sports gambling. Now, you're going to do what you're going to do. So, and on top of that, it's really not my place to give any sort of opinion. But using these sports odds might help you determine, if you're feeling lucky or not. Right, now, again, I'm not going to read all of this, but I'm putting this on the notes, and hopefully you will. Um, let's do this instead. Um, I don't like the way I snipped this. I'm going to snip it down to here. That way things will look a little bit better. All right, so probably didn't have to do that. Didn't have to do that. But I like things to look a little bit nicer and neater. Um, but the main thing we're going to look at here is just basically the odds here, right? The odds in favor and odds against. So the odds in favor of something happening are the probability of something happening divided by the probability of it not happening. And of course, the odds against is the exact opposite. The odds against an event A occurring happen is the probability of it not happening over the probability of it happening. Okay, so I don't think it's too bad, maybe. Alright, so calculating odds here. So in the game of American Roulette, a wheel is spun, and ball The wheel spun and ball is rolled so that it lands in one of 38 colored and numbered pockets on the wheel. There are 2 green pockets numbered 0 and 00. The rest of the pockets are labeled 1 through 36, alternating between red and black. So A reads, calculate the probability of the roulette ball landing in a red pocket. Okay, so if it reads the rest of the pockets are labeled 1 through 36, alternating between red and black, then half of them are red and half of them are black. So if I were to calculate the probability of the roulette ball landing in a red pocket, well, then I say that let's do A. The probability of it landing in a red pocket is 18, and there are 38 possible outcomes, right? So because again it's 36, and then the 2 other ones, the 0 and the 00, so that makes 38. So 18 out of 38, so that's 9 out of 19, and we can't reduce any further, so 9 out of 19. So the probability of us landing in red is 9 out of 19. B, calculate the probability of the roulette ball not landing in a red pocket. Okay, well, if we looked at, if it's, the probability of it landing in a red pocket was 18 out of 38, then we take the complement of that, right? What remains? It would be 20 out of 38, right? So we would say 20 out of 38, or in other words, 10 out of 19. Okay, so that's the probability of it not landing in a red pocket. And then it says A again, so it probably means C, so we'll go ahead and put C. Calculate the odds in favor of the roulette ball landing on red. Okay, so what are the odds of it landing on red? Well, the way we do this is we say the probability of it landing on red divided by the probability of it landing not on red, right? That's what, right, again, let's go back here and look. Calculate the odds in favor of the roulette ball landing on red. All right, we're looking for the in favor. So we're going to say the probability of it landing on red divided by the probability of it landing not on red. So it's going to be this probability of it landing on red divided by the probability of it not landing on red. So we're going to say, and let's actually move this down just a tad so we can work with our fractions. So the probability of it landing on red divided by the probability of it not landing on red. Okay, we know that that's the same thing as saying, we can multiply by the reciprocal. So times 19 over 10. All right, doing the arithmetic here, we know that the 19 cancels out, so we're going to end up with 9/10. Okay, and then that's not a 90% chance, right? It's not a 90% chance that well, okay, never mind. Yeah, calculate the odds in favor of roulette ball landing on red. Yeah, 9 out of 10. Sorry. Or we could write that as, and this is what I was trying to get at, was we could also write that as 9 to 10. Those are the odds, 9 to 10. It'll happen 9 times for every 10 times it won't. That's what that means, and that's what all this over here kind of tells us. Alrighty, and then I think the last one. So finding probability given the odds. So this is they were talking about a Kentucky Derby winner earlier, so we're not going to touch on that because we're just kind of lost now, aren't we? Instead, we're just going to put this probability up here, and then we're going to look at the example. We're going to follow along with the example. Let me go back and make make double sure here. Okay, yeah. All right, so there's a super duper easy way of doing this. If we were to find the well, reading the problem, Dominique sees that his college soccer team has a 3-2 odds in favor of winning their game this weekend. What is the probability implied by these odds? Okay, well, if it's 3-2 in odds, the odds are 3-2 in favor of winning. All you really need to do is take that first number, which is 3, and then divide it by um, that number plus the odds number here, which is 2, right? And that's exactly what this is saying here. So let's um, let's color coordinate this real quickly just to kind of follow along. Um, let's do the probability of some A happening. And we're going to make N be blue, so N over N plus M. Okay, so if I'm going to calculate the odds for example 12, then what I would do is I would say, okay, so it's 3 over 3 plus 2, or in other words, 3 over 5, or in other words, 0.6, or in other words, 60% chance. Okay, and that's how you find probability given the odds. And I believe that does conclude today's lecture. Yes, that concludes today's lecture.